to be here. It's an honor to be invited by you, and I'd really like to express my thanks to the folks who organized this symposium and the events of this 3-day weekend. I know it takes a lot of time and dedication to do that, and I think we're seeing that your hard work is paying off. And again, thank you. It's an honor to be amongst so many great botanists in this room. I actually did not receive a graduate student award, nor am I a herbarium director, but I do have a graduate degree in botany, and I did live in California for 8 years. My first professional position with the U.S. Forest Service Pacific Southwest Research Station located in Riverside, California. And wherever I've lived, I've always tried to become at least a decent amateur botanist and natural historian. And so I moved out there after getting my PhD at the University of Illinois in 1981. Immediately bought all the Jefferson Manual and other local floras and so forth. And off I went up into the hills. And I remember very well one of my first experiences when I was trying to key out a plant that I eventually figured out was an astragalus. Well, there aren't too many astragalus in Illinois. It was a new genus for me. And then it turned out there was something like 98 species of astragalus. And so this happened with every genus I was able to key out, and I knew I was in trouble very quickly. And it was a very humbling experience to be exposed to California flora, and I knew from then on I would stick to trees, which I have done faithfully for the rest of my career. Okay, I am not going to talk a whole lot about individual plant species today, or even about California. I'm going to talk at a much broader scale. So I hope you'll indulge me with that, but also see the relevance to some of the other things we're talking about at the symposium today. After I gave Tom my title, I realized it was too late to change it. I kind of had second thoughts about the word jerks. It really doesn't apply to people. It could apply to people. It could apply to certain Fox News analysts or politicians, CEOs of certain companies or whatever. But in fact, I'll try to demonstrate the relevance in just a few moments. Just to get us started, there's enough gray hair in the room. I think some of you will recognize these characters. It's got an upper right-hand corner. The TV series Dragnet, or Just the Facts, was a very common term, and I just want to kind of get us rolling here, and I think you'll see the relevance later. But 2012, now you might remember that this was the biggest drought the U.S. has ever had, at least in the last century or so, in terms of its overall magnitude and spatial extent. And it was the warmest year since 1895. And it had the highest monthly mean ever measured for July. Globally, it was the warmest year on record, and 8 of the 10 warmest years have occurred since 1990. Last year, more area burned in the western U.S. than in any other year on record, so that's almost a century. And crop yields were reduced in 80% of U.S. agricultural lands. In fact, that had such a big impact that it affected exports and actually dropped the GDP of the United States. So if anybody thinks 1 year of an extreme event can't make a difference, last year was evidence that it can. And 1 year does not demonstrate that it's a manifestation of climate change. But if the temperature continues to increase as it has been, we can look forward to a lot more 2012 in the future. And I'll try to talk a little bit more about that now. So where did this study by Jerks term come from? I like to look to other fields sometimes for models of how I look at natural resources. And one of my former colleagues was a fellow named Ray Daniels, now passed from NC State. And he was a great geomorphologist. And he had this statement about geomorphic development, not meaning the steady, gradual change, but he said it was steady by jerks. So you had these occasional things that happened that were very important. So you see the nice photo there of a stream moving through a mountain system. You have all these gradual things happening with water erosion and so forth. But occasionally you get a big landslide. Or occasionally you get a volcano. And these are the things that really make big changes in geomorphic evolution. Similarly, we have a really good example of an evolutionary model. And I realize I'm a rookie with people who really know about this topic, but I think most of you have probably heard of punctuated equilibrium. It was based on a classic paper by Niles Eldredge and Stephen Jay Gould in 1972. And the idea here is that most species don't have a whole lot of evolutionary change, at least over geologic time. But when that change occurs, it is restricted to rapid events of branching or speciation. And you see the diagrams there kind of indicate this is kind of our traditional view. We get these gradual changes over time. And now these guys come along and say, no, it happens quickly and periodically. And those are the biggest changes that we have evolutionarily. And just an example here of how this might occur in butterflies. So again, gradual change here, the rapid changes here. I tried to find an example for plants, and at least at that time, the zoologist had such a, they had captured ecological theory and evolutionary theory. I don't think that's the case anymore. Anyway, that's why I have butterflies rather than a nice plant example. Anyway, these have been models for me to demonstrate in a broader sense, I think, how climate change is going to affect forest ecosystems and ecosystems in general of North America and the world in general. An awful lot of what you see published about climate change effects is about some small changes in phenology or slight changes in species distribution and so forth. Those are important, but they will be totally overwhelmed by the changes that we will experience and may already be experiencing in disturbance regimes in ecosystems. Let me just go over a little model of how I think this works. Here's a model of how we go from climate change, habitat change, ultimately species responses, and we have another route here that goes through fire in this case. Could be other things there like insects. Now, tree species, which is mostly what I'm going to talk about today in terms of forest ecosystems, trees are pretty tough organisms, right? They grow to be hundreds, sometimes thousands of years old. They survive all kinds of different climatic changes, and they survive all kinds of temperature changes, diurnally, weekly, monthly, annually. So it's going to take a while to change that response along this side here. Now, fires reset succession. They essentially clean the slate, and that's where the action will be, that regeneration phase of which plant can win the battle to establish in that next cohort. So essentially, going this way, this disturbance pathway is a lot faster. So this is an evolutionary change, but it is an ecosystem change. And ecosystem dynamics will go a lot faster if we change disturbance regimes. So let's take a look at this just first of all theoretically. This is our good old probability curve here. And you can put anything you want on the y-axis here. You can put fire, insects, invasive species, so forth. And so if we change the temperature, we can look at various statistics of what that means. And we can look at the mean here. We can look at standard deviation. We can look at this extreme. And what happens when we bump this curve over a bit, okay, we change the mean, so maybe the temperature goes up 2 or 3 degrees centigrade. I am not particularly worried about this. I am very worried about this. So something that used to be a 1 in 40 year event now becomes a 1 in 6 year event. Think that might affect ecosystems? So that's why I really think this is where the action is. And we need to really start trying to focus on how these things will affect our ecosystems. In addition, thresholds are terribly important. And it's the thing we know perhaps least about. We know very little about audicology and physiology of probably 99% of our plant species. And yet changes in phenology, changes in having mismatches between flowering and pollinators and so forth is going to be critically important in species survival in the future. And when we go beyond these thresholds, we often get into unknown territory. Yes, we have this variation, but if we go permanently above this line, that's where we're going to see some things happen that are probably fairly unpredictable. Now, I'm going to show you a pair of photos here that have become rather iconic relative to the exceedance of thresholds. This is pinyon juniper in the Jemez Mountains in Mexico. And so pretty much all the tree species you see there are either pinyon pine or juniper species. This is a shot in October 2002, and this is what it looked like a year and a half later. This is after an extended drought period. Trees became stressed, pretty much shut down. Ips beetles came in and finished them off. Now this is at the lower end, lower elevation distribution of the population, so it's not like all of pinyon pine is wiped out or will be wiped out soon. But it does indicate here that these are trees that are very well adapted to arid conditions. And yet the drought was severe enough and long enough that it pushed them over the edge, and now we have these stands that are having a really difficult time regenerating in some cases. So maybe we're permanently beyond that threshold. We'll see. Here's another very important factor right now in Western North America mountain pine beetle. This is not actual size. If you see one that big, let me know. It's actually about a fifth the size of your thumbnail. But this has become kind of the poster child for the effects of temperature increase on ecosystem disturbance in Western North America. The thing that has changed for this critter, the thing that his life is going really good right now, is this warmer temperature has truncated its reproductive cycle, which is typically 2 years, to 1 year. So imagine what that does to reproductive rates. So you have more beetles, you have fewer of the larvae getting killed in the winter, so we've exceeded some threshold there for the reproductive biology of this insect. And it has greatly expanded its geographic range, not only within its favorite species to eat, like lodgepole pine and ponderosa pine, but also a group of other species, like bristlecone pine, whitebark pine, foxtail pine, which it had never been recorded in attacking previously. So I just took this to remind me, last year my wife and I took a trip across the northern border of Washington from west to east on Highway 20. Some of you may have visited that area. And there was not a single mile on that whole route where you couldn't step outside the car and see a dead tree, dead stand, due to either mountain pine beetle or fire. This is over 300 some miles. So disturbance is really reaching out with these warmer temperatures. We're starting to see it in some of these landscapes. Just a little bit of data here. This is from the Okanogan-Wenatchee National Forest, which is in north central Washington on the east side of the Cascade Range. And what we can see here is some mortality data for mountain pine beetles. And it's just kind of bouncing along here in the 80s, bumps up a little bit in the 90s, and then boom, big increase after 2000, after a long, it's not an extreme drought, but kind of an extended low-level drought period. And what happens with these critters is, after their populations reach a certain size, they can also attack not just stressed trees, but healthy trees. And that's another reason why the populations can expand so quickly. So this is mostly lodgepole pine, ponderosa pine. Here's an example of whitebark pine. Again, bouncing along, low level, and all of a sudden it takes off. So now whitebark pine, Pinus albicollis, is being attacked not just by mountain pine beetles, but by white pine blister rust, an exotic fungus. So that's a double whammy on this iconic subalpine species. This is, at least in the Pacific Northwest, is typically the highest elevation tree species. So how long this species can hang out, we don't know. It was actually proposed for endangered species listing, which I think didn't actually happen. Just a little bit more data. This is for the entire western U.S. Mountain pine beetle attacks. We can see down here 2000. You have this almost linear, bordering on exponential increase in the number of acres where trees were killed. Big hot spot here in Colorado, northern Rockies, along the Cascade, east side of the Cascade Crest. And the very interesting thing is, look what happened in 2011. And we're starting to see in the last couple of years that the number of acres affected is going down. they're running out of food to eat. That basically the stands that were sufficiently old enough and stressed enough to be attacked were running out of that acreage. So we're seeing kind of a threshold again being achieved here. So we got up here to some 8 million acres, around 3 million hectares. But this is nothing compared to British Columbia. This takes a second to load up. What this is going to show you is a time series of the percentage of pine volume killed, lodgepole pine in British Columbia. Just watch this for a few seconds. This is all observed. Now we're going into what's projected, and you'll see those little red lines continue to extend outward. But what we have as of 2013 is approximately 30 million acres of lodgepole pine that have been killed. That's about 12 million hectares. So that's like, what, 40? That's the area of about 40 to 70 national parks. That's a significant land area, most of eastern British Columbia. This is a huge threshold change in these ecosystems, and there's a lot of questions about what happens next. They're doing some clearing of the dead timber and so forth, but it's very unclear how this will play out in the future. Anyway, major changes in ecosystems due to insects. Now I'd like to talk about one of my favorite topics, which is wildfire. That's the thing I spend the most time on. And in order to project what we think might happen in the future, we have to take a look at what happened in the past. So how has the variability in basically warm and cool over the last century or so affected wildfire? And I'm going to focus on the western United States. So this is one hypothesis. This was actually published, and we thought maybe we could use this as a foundation for an NSF proposal. But it didn't get past the first review, of course. So, has anybody heard this term, Pacific Decadal Oscillation? I know that Aaron has, so, okay. So, anyway, it refers, it's kind of like El Nino on steroids, right? So it's based on ocean temperatures in the Pacific and their variation over time. And bottom line is, what it gives us is these alternating, generally warm and generally cool periods of about 20 to 35 years or so. It's kind of a pseudo cycle, because you can see that even during cool periods you have warm years, even during warm periods you have cool years, and we may now be kind of going into a cooler cycle. But it has a tremendous effect on especially winter precipitation as well as temperature. And we've used this as a basis for trying to look at climatic variability in the West. What I'm showing you now is some data on wildfire area on federal lands for the western United States. This is just the 11 big western states since 1916. And so this is hectares on this side, acres on this side, take your pick. And what we see essentially is this pattern of basically a lot of fire, not much fire, and a lot of fire. And this has usually been explained by, well, there was this big period of wildfire after settlement by Europeans, and we did a good job of putting fires out, fuels accumulated, and now that it's getting warmer, again, we're burning up those fuels and we're getting more fire burn. Anybody heard this explanation? Students surely have. Well, being the eternal skeptic, I superimposed the PDO cycles on this, and I think it's a decent correlation. You know, I'm not a big believer in coincidences, so my inference here is that this climatic variability in these warm and cool periods have a big effect on wildfire patterns in western U.S. Now, that is not to say that climate change is not and will not be a big player. In fact, I think it reinforces it. Because if the climate continues to warm at the current rate, then we are going to see a lot more periods of time that look like a warm PDO, basically more wildfire. So this is just a very simple regression-based, empirically-based model of what we think it could look like by about the year 2050. and they're referenced to the period 1970 to 1999 in terms of the percentage increase by this year. And basically, the more red it is, the more fire we expect. I don't take these numbers too literally. If you look at California here, we're in about the 200% range or so. The interior west, we're looking at much higher increases in area burn. So these are just empirical projections. There's no processing built into this. It's just kind of a little look into the future of having more wildfire. But the bottom line is, throughout the West, we really do expect we'll get 2 to 3 times more area burn. The agency I work for, U.S. Forest Service, currently spends 53% of its total budget on wildfire management. Most of that's spent on fire suppression. Most of that is spent on protecting structures, homes, buildings, and so forth. So if we take that 53% and then we double the area burned, that's real close to 100%, assuming a linear relationship. So that kind of policy is not really sustainable. I figure on Saturday, nobody at the higher levels of my organization is here to hear me say that. Another model that I'd like to use, I borrowed from plant pathology in terms of trying to express how stress can affect ecosystems. This is something called the disease spiral that was developed by Paul Mannion, who's a forest pathologist in Syracuse. And he basically looked at tree mortality as an accumulation of stresses over time. So you have all these different things, I know you can probably hard to read in the back, relative to insects and pathogens and droughts and so forth. And relative to climate change, it is one of many stresses that trees and forest ecosystems face during their life. And it takes all these things built up typically before you actually kill a tree or kill a forest stand. And I refer to these as stress complexes. They're mediated by climate. The climate is a forcing factor, but it does require these other cumulative stresses. So just as an example, I think Nick's conifer in Sierra Nevada and Southern Cal is probably one of the best examples of a stress complex, because you have all these different things going on that can potentially build up and kill a tree, kill forest stands. And just to show you what's on the screen here in a little bit more of a box and arrow fashion, we start up here with global warming, and it sets off this chain of other events. So we have higher temperatures, which causes extended droughts. That lowers the vigor of trees, which allows bark beetles to come in. Bark beetles can kill trees themselves, or they can, at least in the short term, cause accumulated fuels that lead to more severe fires. And then you might get some change in species composition, increased invasive species, and so on. So this is just a diagrammatic model of how things interact, but the impression I want to leave with you is it's not just one thing, it's not just climate, it's not just insects, it's not just fires, it's all these things together that are going to change our ecosystems in the future. And it's not always simple, it can be very rather complex. So is there anything we can do about this? This is a photo from the tripod fire, which occurred in northern Washington in 2006. It was a 175,000 acre fire. Lots of variation in the landscape, as you can see here. And so with a lot of these large fires occurring in the western U.S. in the last 10 years or so, we've had fires up to 500,000 acres. People have been asking, well, what can we do? And one suggestion is, well, we can go from these dense stands that have had fire excluded for many decades through active management to something that's a little bit more open. I know some people find this like an offensive photo because it's so open, but what has happened here basically is not just a reduction in tree density, but also a removal of surface fuels. So this is probably more like what a lot of our dry forest stands looked like prior to 1900, when fire burned every 5 to 10 to 20 years or so, removing some of that understory vegetation and reducing stem densities. And there's good evidence of why active management would work to do this sort of thing. Again, this is from the tripod fire, where we did a lot of follow-on studies, and Here's an area that didn't have any pre-fire treatment, had essentially 100% tree mortality, and areas that had thinning and prescribed burning prior to the wildfire had about 80% survival of the residual steam. So you can do this. We know this works. There's plenty of evidence for it. The question is, do we want to do it, and at what scale do we want to do it? This is at higher elevation in the tripod fire, so this is up in kind of lodgepole pine and some subalpine species, which were clear-cut in the past. And in fact, the only green places left on this landscape are the areas that were clear-cut. But they also removed the surface fuels. They removed that splash after they cut it. So these are essentially a source of biodiversity in an otherwise almost completely 100% mortality landscape. So I like when I give a talk to people like I did at the Sierra Club this last Monday, I like to put this up just to get their attention. It does indicate that creating some diversity in this landscape may have benefited from the past active management in this landscape. It depends on what you want, right? It depends on what species you want, depends on what kind of biodiversity you want, depends on what spatial patterns you want. So these are choices that we make. But the challenge here is how do we do this at a large scale? It's pretty darn easy to do for a small stand, but can you actually do this across tens or hundreds of thousands of hectares? And recently we published this guide, we're calling it a national guidebook for the national forest, on how to do climate change adaptation. This is more strategic than tactical, so it goes into great detail about how one might actually do this. But we're finding that a lot of our resource managers are becoming more interested in taking this from a conceptual idea to an actual on-the-ground implementation in how we do resource management. And no, it's not just about clear cutting. So I'm just going to go through a few things here, a few ideas about things I think we could do if we choose to, that I think would help transition ecosystems over this next century of increased temperature. One thing is to increase landscape diversity. The thing is, it takes a lot of effort and time to do this, but if this is something we want to do in dry forests, we can reduce the density of some of these forests to something more like what they were prior to 1900. We can also increase biological diversity, and what I mean here is where we have an opportunity, say, to plant trees. Maybe we plant genotypes that are outside of the designated seed zone. So, scientists spend about 40 years developing these seed zones, and thou shalt plant from this seed zone, right? Because your seed stock would be best adapted to that location. Now we're saying, well, maybe we need to rethink that a little bit. So you may want to plant the seed zone south of where you are, or a lower elevation where you are, in addition to the native trees, the local seed zone. So you create some diversity. So if something occurs, a drought, insect attack, or whatever, you don't lose the whole thing. You'll have at least some survival. This is an idea. It's not being used very much yet, but I think we'll see it coming. Increase resilience at large spatial scales. It's great to do these small projects, but the fact is, unless you do this across very large areas, you'll have little opportunity to really change the spread of fire and insects across large landscapes. It's nearly impossible for the agencies in the western U.S. to generate the funding to do this at a scale that will make a difference right now. So this is, I won't say it's conceptual, but it's a little bit of a dream at the moment. Point is, if we're going to do that, do it strategically. We tend to think of these large wildfires as disasters or catastrophes. The media kind of spreads that word, right? Of course, fire is a natural occurrence. It will be a matter of not if fires occur, but when fires occur. So let's plan for them. Let's know what we're going to do if we're going to do something in an active management way right after the fire. Get those plans approved so we can hit the ground and do some things, including this diversity of tree planting, for example. Early detection, rapid response is kind of a fancy way of saying, well, after a fire or some disturbance, get out there and see what's happening, monitor it, collect some data. If there are invasive species, let's try to get them out of there if we can. and then continue to monitor for a while so we can see what the effect of these larger disturbances is going to have across these large landscapes. Now, I've said very little about species today. And I know botanists, to a certain extent, including myself, are all about species. The reason I didn't isn't because species are important, but I think in the future it will become very difficult to protect species, and that we may need to focus more on functionality and processes of ecosystems as the things that we designate to protect. Things like the Endangered Species Act have done a tremendous amount of good, but they're in some ways almost restricted in a dynamic world. They were written with very static rules. And if we are going to have species start to move around the landscape, and if we're going to have big fires and other disturbance machines affecting them, it's going to be very challenging in the future to protect all of these different critters. So, there's the question of whether or not we should do this sort of active management. And I often feel compelled to defend our resource managers and federal and state agencies because they've got all this science they have to learn, they've got all these people beating on them with different agendas and so forth. And so they feel like they want to do the right thing, whatever that is. So you're damned if you do, damned if you don't. So what I would suggest to you is to take the resource manager to lunch. Probably better off taking for a beer, him or her for a beer, because then they need some counseling. But basically, we need to continue to have this discussion so that we can connect science with management, knowing that the future is very uncertain right now. So some of you have probably seen this cartoon before. It came out shortly after the climate gate in 2008. And I like this because it reminds me there's a lot of things that we can do in conservation and resource management that are very good. The sustainable resource management, I really believe in that. And things that we can do that promote sustainable resource management will generally also promote climate change adaptation and the transition of ecosystems into a warmer world. So I use this as a reminder to myself that yes, there's hope, and probably about 75 to 80% of everything we're doing now is helpful for moving us into a greenhouse world. So we've got to remember the positive ideas here, and not just focus on the gloom and doom of what could happen 100 or 200 years from now. So that's it. I don't know if we have any time for questions.
Questions if you have some, and otherwise after the questions we'll have a photograph over here and you will all eat lunch and come back by 1:20. Any questions?
Yes, sir.
Yeah, at one point you're talking, you showed your Gaussian distribution of shift in climate, and your emphasis was on the extreme events, and I think totally agree with that. It's a great point. Although you said you weren't as concerned about the mean shift in temperature, I would suggest in some cases that mean shift can be very, very important for management, such as along what's happening in ecotones where they're already on the margin. And then in cases with phenology and plants, effectively timing flowering, pollinators used to be very disruptive. So in some of those cases, the mean also I find the shift to be a little disconcerting.
So the comment was that shift in the mean on that curve that I showed you is also important for things like phenology, plant species located in ecotones, and so forth. And I totally agree with you. I didn't mean to dismiss that. I was just trying to get us moving towards the effect on that extreme end. So I think we definitely need to study and monitor both the mean as well as the extreme and everything in between. The problem is we don't know enough about the response threshold to most of our species to know exactly where to look. So we need to keep probing some of that basic science on audicology and plant physiology. Yes?
Somebody that works on the species in the things, the whole idea of trying to re-engineer our, natural habitat with species or with populations from downslope or from different locations. It kind of presupposes that we have an ideal taxonomy already. Finding, trying to have some of these, a lot of what we thought of as pretty widespread species are very tractile and have might have very narrow, much narrower ecological tolerances within ancient lineages that have all been treated together because of lack of resolution in the taxonomy. And we start moving things around and we really run the risks of hybridization and extinction of local endemics. I mean, we don't even really, it's like these situations where we have to do something, there's definitely the potential to do things that are destructive in the best intentions. And that's one of the things that we worry about in taxonomists we worry about, because there isn't a general perception that our taxonomy is reasonably good, and I think it is reasonably good, but there's a huge amount that still needs to learn.
So the comment was, we may need to use some caution if we start talking about moving species around the landscape. Because often we get this thing in our head of, where we are now is we're some perfectly evolved point in time. Everything is exactly where it should be, when in fact there's a lot of variability or lack thereof in certain species we don't understand. And that if we start tinkering, then we could make bigger mistakes than if we just left things alone. I've talked to a lot of different groups, especially in the fish and wildlife agencies about this, and they usually use this term assisted migration. I guess it's kind of the generic term for moving things to where you think they will survive in the future. And there's interest, but very few people seem to want to actually do it. They don't want to be the one who's going to make the decision to move that critter to some place. Having said that, I see a lot more willingness to think about that in some of my friends who work with Pacific salmonids, many of which will almost certainly become extirpated in the next few decades as stream temperatures change in the Pacific Northwest. So I don't know how much will there will be to do this sorts of experimentation with species, but I think it's a tremendous point. We have to be awfully careful. Question? Back there?
I'm sorry, I can't figure out how to phrase it as a question, but I just got to say the whole idea of forget about species and manage for greenness.
Is it?
Yeah, well, so I guess the question is, you said that maybe it's time to pay less attention to species and manage for ecosystem function and other higher level characteristics. And I wonder.
Okay, I think what I said was in the future it will become more difficult to manage for species because we have thousands of species and there may be some aspects of the functionality of ecosystems that we can retain. Just to give you an example, and if I said this in the Pacific Northwest, I would probably get shot, but northern spotted owl, which also has spotted owl in California. And so if we remove northern spotted, if they go extinct, they become extirpated in a particular area, probably nothing different will happen there in terms of the functionality or processes of that forest ecosystem. That doesn't mean we want them to go away, but that their disappearance will probably not affect the overall functionality or affect other species very much, as far as we know. But I think those sorts of things, these local extirpations of species, may be so subtle or may occur so quickly that we can't detect them. But there may be some things that we can do at large spatial scales to create the habitats and sufficient variability across large landscapes to support those species. So I guess I'm kind of looking from the top down rather than the bottom up, but I think we agree on the goal. Yes?
So maybe just to follow up on that with less of an emphasis on species. So is the Forest Service able to do anything, or are they doing anything to save Pinus albicollis in the Rockies?
Yes, that's a very good question. There is currently a gene conservation project, and I don't know, Aaron may know something about that. You work with Rich Crum, right? So there's a group of scientists with a gene conservation project for Pinus albicollis, Pinus aristata, and maybe Pinus balfouriana, I'm not sure. But they've collected seeds, they're growing trees, they're trying to understand the genetic variability of species in terms of specifically their resistance to white pine blister rust, but also more broadly about the ecology of these species. And there is a plan to, as we get a lot of mortality in albicaulis, that we can plant some of these genetic stock that actually have some resistance. Now that's a long-term project, and it's a heck of a lot harder to do that where those trees live than when you would at lower elevation, easily accessible areas. But we're doing a pretty good job on the genetics of that species, and that's just a small project. I don't know if we can do it at a scale that's large enough to make a difference, but the Forest Service does have a lead on that.
Okay, I want you guys to look at your neighbors, find out if there's a resource biologist next to you, and find me lunch.